But riding thermals may not be as easy as it looks. A thermal is quite a narrow column of rising air, and to stay within it, a vulture has to make quite sharp turns, and that can lead to disaster.
Right now, you think gravity is pulling you down, but here's the truth that's going to change everything. Gravity isn't a force. There is no pull. You're actually being pushed up through curved space-time. And what you call weight is just resistance to your natural path through the universe. Let me explain what's really happening. Space and time aren't separate. They're woven together into space-time, a four-dimensional fabric that makes up reality. And massive objects like Earth don't pull on things. They curve this fabric. Think of a trampoline stretched flat. Put a bowling ball in the middle and it creates a dip. Roll a marble near it and the marble curves toward the bowling ball, following the slope. That's what Earth does to space-time. Here's the wild part. Right now, sitting in your chair, you're not at rest. You're trying to move through time. Because Earth has curved space-time, your natural path, the straightest line through this curved geometry, would take you toward Earth's center. That's your geodesic. But the floor won't let you. Electromagnetic forces between atoms in your body and atoms in the floor push up against you, preventing you from following that natural path. That push, that resistance, is what you experience as weight. You're not being pulled down, you're being pushed up. This is why astronauts in orbit feel weightless. They're not beyond Earth's gravity. The gravitational field at the space station is still 90% as strong as on the ground. They feel weightless because they're finally free to follow their natural path through curved space-time. They're in freefall. Nothing is pushing on them. They're experiencing their natural state of motion. The normal state in the universe is freefall. Sitting still, feeling weight, that's abnormal. We've had it backwards our entire lives. This explains something beautiful. All objects fall at the same rate, in a vacuum, regardless of mass. On the moon, a feather and a hammer hit the ground simultaneously. In Newton's framework, that's a weird coincidence. But in Einstein's framework, it's obvious. Objects aren't being pulled by a force proportional to their mass. They're following geodesics through space-time. The curvature doesn't care about mass. A feather and a boulder follow the same paths, so they fall at the same rate. Natural and inevitable. Einstein figured this out through pure thought. He imagined being in an elevator in deep space, accelerating. He realized you couldn't tell the difference between that acceleration and gravity. If you dropped a ball while the elevator accelerated, it would fall to the floor just like on Earth. From that simple insight, he built general relativity. Mass tells space-time how to curve. Space-time tells mass how to move. It's a feedback loop, creating all the motion we see. Planets orbiting stars. Stars orbiting galactic centers. All of it is objects following the natural contours of curved space-time. Now here's something that will blow your mind. Time itself is affected by gravity. The stronger the gravitational field, the slower time passes. This has been measured. In 1971, atomic clocks on airplanes ticked faster than identical clocks on the ground by exactly what Einstein predicted. The difference was tiny, just nanoseconds, but real. Time actually passed at different rates. GPS satellites must account for this. Their atomic clocks run slightly faster because they're higher up where space-time is less curved. If GPS didn't correct for this, your navigation would be off by kilometers within hours. Every time you use Google Maps, you're relying on Einstein being right. Time isn't absolute. Two people experience different amounts of time depending on where they are in a gravitational field. Near massive objects, this gets extreme. Near a neutron star, time passes 30% slower than far away. Near a black hole's event horizon, time slows so much that from outside, it appears to stop. Someone falling in would appear to freeze just outside the horizon, fading from view. But from their perspective, they'd fall through normally. Two different realities, both true, depending on your viewpoint. Black holes are the most extreme example of curved spacetime. They're regions where spacetime is curved so severely that nothing, not even light, can escape. Not because something is pulling really hard, but because spacetime itself is curved so much that all possible paths point inward. Once you cross the event horizon, every direction leads toward the center. There's no way out. The geometry itself has been warped to where inward is the only direction that exists. Inside a black hole, the future literally points toward the singularity. You can't avoid it any more than you can avoid moving forward in time. Let me tell you about gravitational waves. Einstein predicted that accelerating masses produce ripples in space-time itself. Waves that travel at light speed, stretching and squeezing space as they pass, for decades, purely theoretical. Then scientists built LIGO, using lasers to measure changes in distance smaller than a proton's diameter. On September 14th, 2015, both detectors picked up a signal. A gravitational wave had swept through Earth. Two black holes, 29 and 36 times the Sun's mass, had spiraled into each other 1.3 billion light-years away. In the final fraction of a second, they merged. Three solar masses converted entirely into gravitational wave energy. In that moment, more power than all stars in the observable universe combined, and we felt it. We measured space-time itself rippling past us. Since then, dozens more detections, black hole mergers, neutron star collisions. Each one confirms Einstein's equations work, even in the most extreme conditions imaginable. When neutron stars merge, the gravitational wave signal encodes information about their internal structure. These are the densest objects besides black holes. Matter compressed so much that atomic nuclei merge into exotic states we can't create in any laboratory. By studying the waves, we're probing what happens to matter at those extreme densities. We're conducting experiments on physics impossible to test any other way. The universe itself is expanding. In 1998, astronomers discovered the expansion is accelerating. Something called dark energy, making up 68% of the universe, is pushing space apart. We have no idea what it is. It might be a property of empty space itself. And there's dark matter, invisible mass we detect only through gravitational effects, making up 85% of all matter. We're living in a universe where 95% is stuff we don't understand. When astronomers measure how fast stars orbit in galaxies, the speeds don't match visible matter. Stars on outer edges move too fast. They should fly off into space. The only explanation is additional mass we can't see, providing extra gravity. Dark matter doesn't emit or absorb light, completely invisible. But it has mass, so it curves spacetime. Leading theories suggest undiscovered subatomic particles that don't interact with light or normal matter except through gravity. Scientists are building detectors to catch these particles. So far, nothing conclusive. So, what does this mean for you? You're not being held down by an invisible force. You're following the natural geometry of space-time, curved by Earth's mass. The floor is pushing up, preventing you from following that geometry to Earth's center. Weight is resistance to your natural motion through curved space-time. Once you understand that, everything changes. You see yourself not as separate from the universe, but as part of its dance, moving through four-dimensional space-time, following curves written by every massive object around you. Those atoms in your body are ancient, forged in stars that died billions of years ago. Those stars exploded, scattering atoms into space. Gravity brought them together again, forming new stars, new planets, eventually you. The carbon in your cells, iron in your blood, calcium in your bones, all came from stellar furnaces and supernova explosions. You're literally made of stardust, and you're here briefly, cosmically speaking. But in that blink, you can understand we've built instruments to detect ripples in space-time from colliding black holes billions of light years away. We've imaged black hole shadows. We've traced cosmic history back to the Big Bang's first moments. You're part of a species that figured this out. That's extraordinary. The universe is vast and complex, but it's comprehensible. We can understand it. We are understanding it. The next time you drop something, remember it's not being pulled down. It's following the natural curve of space-time. When you look at the moon, it's in freefall, circling Earth, because that's the geodesic it follows. Through curved space-time, Earth creates. When you feel weight in your chair, you're not being held down. You're being pushed up, accelerated through space-time by electromagnetic forces, resisting your natural path. You're surfing the geometry of the cosmos. And once you see it this way, the world becomes more alive, more connected, more beautiful. That's the gift of understanding gravity, not as a force, but as the shape of reality itself. You're not stuck to Earth, you're dancing through curved space-time. And that changes everything.